Hello, today we have these two problems. Let's begin with the first one. So derivative of f is just f but plus some constant, so when we differentiate both sides with respect to t, we're gonna have a very nice equation that implies that f prime of t is some function of form c times e to the power of t, and we can find the original f of t with constants through this. Also, the reason this video is so late is because I have been obviously busy, but I don't know what time zone you have, but in my time zone it's still the perfect calendar date, so I'm not like, I have not broken the old, the challenge is still going. So now let's mark both constants entrance with C1 instead of just C. It's nicer, more systematic. And now let's plug this into the original equation to find the constants. So we're gonna have this equals, and let's find the definite integral real quick. Oh wait, let's just write the brackets instantly. It's gonna be something like c1 times e plus c2 minus c1. So obviously this cancel. We have just 0 equals 2 times c2 plus c1 times e minus 1. Now let's express c2 in terms of c1. We're gonna have c2 equals c1 times 1 minus e over 2. So the function is gonna be equal to c times e to the power over t plus c times 1 minus e over 2, and c is some real number. Cool. Let's continue. Have to evaluate these three limits. Let's begin with this one. So obviously this can be expressed as a fraction, and we can apply L'Hopital's rule because both the denominator and the numerator are gonna be diverging as x approaches infinity. So let's do that right away. I'm gonna have a limit as x approaches infinity of e to the power of x squared over 2x times e to the power of x squared. E to the power of x squared is going to cancel out. We're going to have 1 over 2x, and that's obviously going to just be 0 as x approaches infinity. Okay, let's continue. We have this limit. Now, let's first deal with this quirky definite integral. It's really annoying to deal with. So let's rewrite it. I have from x to 0 of e to the power of t squared dt, plus from 0 to x plus 1 over x of e to the power of t squared dt. Now the thing is, for the first one, we can swap x and 0 and just negate it. That would still hold true. So let's go back to the limit. Now, I could write down everything after applying L'Hopital's rule, but we have already calculated this limit, so I don't see any particular reason to write down this term. Let's only go with this one. We're gonna have e to the power of x plus 1 over x squared times the derivative. It's gonna be 1 minus 1 over x squared all over 2x times e to the power of x squared. So let's continue with the limit evaluation. We're gonna have e to the power of x squared times e squared times e to the power of 1 over x squared times 1 minus 1 over x squared over 2 x times e to the power of x squared. No, e to the power of x squared is gonna just cancel out. Next, we can pull out e squared and 2 outside. E squared over 2. And let's also rewrite this fraction as multiplication. Now, finally, let's rewrite this limit entirely. Let's instead say that its limit as e approaches 0 from the right. And let's say that p is equal to 1 over x. So we're gonna have e to the power of p squared times 1 minus p squared times p. Now we can just do a simple substitution. E squared over 2 times 1 times 1 times 0. So this is just gonna be 0. We have evaluated the limit. Let's go with the next one. So same thought process here. I'm not gonna write down how I'm gonna transform the definite integral. You know how I would do that, just like the previous time. So let's focus on the interesting part and apply the L'Hopital rule. 2 times x times e to the power of x squared. In the top we're gonna have e to the power of x plus natural of x over x. Well, that is gonna be squared. Times, let's find the derivative now. 1 plus 1 minus natural log of x over x squared. Now, let's rewrite that. It's going to be e to the power of x squared times e to the power of 2 times natural log of x times e to the power of natural log of x squared over x squared times 1 plus 1 minus natural log of x over x squared over 2 times x times e to the power of x squared, and we forget to include the limits. Okay, so let's right away pull out 2 here. Next, let's cancel e to the power of x squared. Now, e to the power of 2 times natural log of x is going to be rewritten as x squared. And let's divide by x, finally. That's going to be the limit. And it looks like something that diverges. In fact, let's review all of this, except for x for now. Let's review this. Say that it's going to be greater than or equal to 1. Let's take the natural log of both sides. We can get natural log of x squared over x squared greater than or equal to 0. This is just a square, so it's always going to be greater than or equal to 0. So let's go with this one. Now, if we were to take really huge values of x, this is not going to be equal to 1. Yes, this would be approximately 1. So let's just prove that now. Let's take the limit as x approaches infinity here. It's just gonna be 1 plus limit as x approaches infinity 1 over x squared minus natural log of x over x squared. Both are known to converge to 0, that's just gonna be 1. Cool. So that means that if we take sufficiently large value of x, this is gonna be sufficiently close to 1. So 1 minus this, yeah, less than or equal to, for example, 0.1, given x is greater than or equal to some value a, who we know exists. Now let's get rid of this. So do you know what it means? That essentially means you can safely say that this expression over here for x greater than or equal to a is gonna be greater than or equal to x times 1 times 0.9, because 1 minus 0.1. Cool. So we have proven that this statement is always going to be greater than 0.9x. And think about 0.9x. For every value that you can think of, you can find some x that would result in the function being equal to that. So it obviously diverges, and since this is greater than that, it's also continuous for x greater than 0. That would suggest that this also diverges. So the limit simply does not exist, or in other words, we can say that it diverges to infinity. Cool, we have solved everything for today. Bye.